This is an example of an AC analysis problem at level 3. So we'll click on AC analysis here. And we're going to illustrate the first type of problem at level 3. And this will be a superposition problem. And it will tell us that up here in the example. So I'm showing an example just to illustrate what this is about. So we're asked to solve this using superposition, and we notice that we have two independent voltage sources. So the first thing we want to do is to see if there are any simplifications that are possible to the circuit before we do superposition. It's always best to do any possible simplifications before we start turning off sources. Otherwise, you'll end up having to repeat the process more than once, and that would just waste time. So let's go down here, and we notice that these two passive elements are in fact in parallel. However, there is a problem because one of them has a sought current, and we cannot combine things with a sought current because that would destroy that sought current. So what we have to do is to do a sought variable transformation, as you probably did back in the DC single node pair single loop tutorial in the upper level of that. And what we do is we change the sought current to a sought voltage by defining a relationship, which in this case is just an Ohm's law relationship that relates I naught to V naught. So we create a new voltage across this, which allows us to delete the old sought current, and we can then recover it using this. And now that they have only a common voltage, they both have the same voltage being in parallel, so that now no longer prevents us from combining those two elements. And so now remember that when you combine impedances in parallel, we have to take the reciprocal of the sum of the reciprocals of each of the two values. So we have the 6 ohm and we have the J2 ohm, the inductive impedance. And we could use the product over some form, but really it's probably easier on a calculator just to use this directly. And then when we compute that, we would get 0.6 plus J 1.8 ohms. And then we look and see, well, are there any other simplifications possible? And in this case, we'd have to say no. So at that point, we want to start turning off sources. So we would, for example, leave the V2 source active, and the V1 source, this one, would have to be turned off. And remember, for a voltage source, that means we set it to 0 volts, which means a zero-valued voltage source is equivalent to a short circuit. So see that that's been changed to a short circuit here, as it says. And of course, if it were a current source, then we'd set that to 0 value or 0 amps. And a 0 value current source is not a short circuit, it's an open circuit because no current can flow through an open circuit. So we would have to remember that if we had a current source, which we don't in this particular problem, but you might get a problem with a current source or one or more current sources. So now we have a child circuit with just one source active, and we always want to try to solve this using single node pair or single loop techniques. Well, it's not a single node pair or single loop, but we do observe that we have two passive elements there in parallel, which can be combined, and that will make it a single loop. So we select those two to combine, and we just use the standard formula. Again, because they're in parallel, we take the reciprocal of the sum of the reciprocals of each value, the negative J3 and the negative J4, and then that computes to a negative J 1.71 on a calculator. Using the complex number capabilities of the calculator, we can do that directly. And so we replace, for example, this one. We could do either one, but I just guess here replaced this one by that value. And the other one has to be changed to an open circuit. Remember, it wouldn't make any sense to change it to a short circuit because then that would be equivalent to having no impedance there at all, and that certainly would not be equivalent to the original version. So having done that then, we now have a single loop circuit, and that's amenable to a simple voltage divider. And so we would use the standard voltage divider formula. And remember that this variable now, the sought variable, is now primed because it's due to one source only. So it's a part of the total V0 variable. That's why it's denoted with a prime. And that's inserted automatically by Circuit Tutor, but you would have to remember to do that if you're doing it on paper. Okay, so we have our voltage source value, the V2S, which is 4 angle 30 degrees volts. And then we would multiply that times the impedance of interest, the Z1 value, which is the 0.6 plus J1.8, which is in the numerator. and then divide by the sum of all the impedances in the loop, which would be the Z1 plus this value, and that's what we've done here. Now remember, the logic of that is simply that the voltage source value divided by the sum of those impedances, in other words, this divided by this, gives us the current in that loop, and multiplying the current times the impedance of interest will give you the voltage across that same impedance, which is what we want. Now, what we always have to be careful about there is to check the polarity. Remember that P word. So we might need a minus sign in front of all this, and about half the time we will need that minus sign. So it's very important to check that. So here we see that the positive side of the voltage source is connected to the positive side of V0, and the negative side of V0 is connected to the negative side of the voltage source. So those have the same sense, this source and that SOT voltage. So therefore we need a plus sign, and that's why there's no minus sign there. And then simply evaluating that expression on a calculator with complex number abilities directly gives us this answer. Okay, then we have to go back and turn off the other source. So now we've turned off the V2S source, replaced that by a short circuit. Remember that V2S was down here, and now that's replaced by a short, and now we're keeping V1S active to find the effect of the other source on the output voltage. So superposition works the same way for AC circuits that it did, for example, in the DC superposition tutorial that you may have done previously, where we applied it to DC circuits. So now, again, we want to try to make this into a single loop or single node pair circuit. And again, this is why we did some of that simplification before we started doing superposition. Otherwise, we would have to do that same simplification that we did originally in two different child circuits, and that would just increase the amount of work. So it's always best to simplify before we start killing sources. So now we notice that, once again, this and this can be combined in parallel because they're connected to the same two nodes. But notice here we have a SOT voltage in this case on this impedance, and therefore this also have the same voltage across it because it's in parallel with the first one. Therefore, we don't have to do any SOT variable transformations in this case. It's easier, and we can just combine those in parallel. So we go down here, and we would just use the standard formula to combine impedances in parallel. So remember, we take the reciprocal of one, add it to the reciprocal of the other, and take the reciprocal of the result. Don't forget that last reciprocal, or you, of course, wouldn't even get the right units if you didn't do that, let alone the right answer. So we have the Z1 value here has been taken the reciprocal, and then the negative J4. And again, just evaluating that straightforwardly on a calculator will give us this value, the 1.85 plus J, 2.77 ohms. And then to combine those, then we just eliminate one of these two elements. Say we eliminate this one, for example, and then also the circuit's been compressed here just to make it a little easier to read. And so so that value, the Z2, basically is the result of this calculation. So that's replacing it. And the other one, of course, is changed to an open circuit, as we always do when we combine things in parallel. So now we can once again use a voltage divider formula because we have a single loop circuit with one voltage source. And so just as we did before for the other source, we put the value of the source, the 6 angle 0 degrees in this case, multiply that times the impedance whose SOT voltage we want to know in the numerator, which is this value, divided by the sum of the two impedances, which is what's in the denominator. And again, remember that the voltage divided by the sum of those impedances is the current in that loop multiplied by the impedance of interest will therefore give us the voltage of interest here, the V0 prime. Now, once again, we have to check the polarity because this is a different source. It may have a different polarity than the other one. But in this case, we see that the positive side of the source is still connected to the positive side of V0 double prime, and the negative side is connected to the negative side. So those have the same sense. So once again, we luck out and we don't need a minus sign here. But remember that half the time, roughly, you will need a minus sign. So it's very important to always check the polarity in the voltage divider formula. And then the last step in superposition would be to combine those two partial values that we had before, which were the 10.7 angle 63.4 and the one from the first calculation for V0 prime, and just add those two numbers on a calculator. Again, you would need a calculator to do that because the result is certainly not obvious, but it's basically vector addition of those two numbers. And that gives us the final value of V0 due to both sources acting at the same time. And then we would do the inverse phasor transform on this. it wouldn't make much sense really to do an inverse phasor transform on the partial voltages because there's no easy way to add those without using trig identities. So it makes much more sense to do that after we compute the final voltage. And so that just becomes 22.5. The value of omega here, omega was given as 0.9 kiloradians per second, so that's 900 in other words, and so that 900 is written there. And then the phase angle is that of the phasor. And of course the units are always given in volts. Now, we did, however, want that value of I naught, which was what we were, I think, originally asked for. If we go back up to the top of the problem, remember it actually is solved for that current I naught. So now we have to do an extra step because we did the SOT variable transformation to take V naught and divide it by the 6 ohms. That was our SOT variable equation, or I'm sorry, the auxiliary equation really for that SOT quantity that we developed earlier. And so we just now divide by 6, and in the phasor domain that gives us this value, just dividing the magnitude by 6. Of course, the angle of 6 is 0, so that doesn't change the phase angle. And although it would if this were a something other than a purely real number, that would change the phase angle. Then we'd have to do the complex arithmetic, and then that will give us the value then, just taking the inverse phasor transform as we did before, will give us the value of I naught of t. So that shows an example. So now let's work an actual problem of that type at the hard or level 3. So now we see that we are asked to do superposition here. And it says we must use superposition to solve this problem. So we basically want to think about, first of all, remember the most important thing is, can we simplify the circuit before we start superposition? You always want to do it now before we start jumping in and killing sources if it's possible. And clearly these two elements can be combined in parallel, and actually after doing that we could also combine the resultant in series. So we definitely want to simplify the circuit before we start to kill sources. Now remember that if you ever need to give up on a problem, you can just click the give up button at any point for no penalty on your grade. You would just have to work then another problem of the same type. Okay, so let's go into the circuit editor to simplify that circuit. And now we need to combine those two values in parallel. So to do that, I will use a calculator. And I'm using my TI 84 Plus emulator here just as an example. If you have a different model, then you would have to make appropriate adjustments. But let's take the, and remember that in order to do this, we must always be in the complex number mode. So we see here that we're in the polar mode. But in this case, we actually want to have a result for an impedance in a rectangular form, because these text boxes require rectangular form. So we're going to actually change the mode here. And if you were in real mode, that for sure wouldn't work. I'm sorry, here, if it said real, that for sure wouldn't work. So I'm going to go change the mode before I start, just to make it easier, to rectangular mode. So I press enter there to select that mode. Clear to exit the mode setting. And now I'm in the proper mode here. So I'm going to take the reciprocal. Now there's 1 divided by, and there's probably other ways of doing this too. Do be aware, however, that in some models, if you like to use the numerator and denominator templates, that those do not always work with complex numbers. It depends on which particular model you have as to whether or not that'll work. So I'm just going to do it kind of the old-fashioned way with the division sign. So 1 divided by, now I'll put parentheses around the entire denominator. So first I need to take the reciprocal, 1 divided by the first value that I'm combining, which is negative j, and of course j is written as I on a calculator, so it's second I. Remember the I is associated with the decimal point key here, but you have to use the second key. So we have I8, and then we're going to add to that 1 divided by parentheses I7, using implicit multiplication as this calculator allows. Some calculators don't allow that, but this one does. And now I need to close that entire expression, and I can click the enter key, and that'll give us the answer of J56. So, and I probably could have really done that in my head. Well, maybe not so easily, but anyway, let's just replace that by J56. And then the other one has to be removed or deleted because that's what you do when you're combining elements in parallel. So we press the delete key on the keyboard here, or you could press delete up here, or I could have also right-clicked and selected delete down here. Okay, so now we'll check that combination. Remember, we have to check each combination one at a time. We're not allowed to do multiple steps here, as the circuit tutor wouldn't know how to check that then. Okay, so now we want to combine these two elements in series. That fortunately is quite easy. We don't really need a calculator for that. I do have to go get my dialog back where it belongs here if I can. Yeah, it likes to jump around when I use less than full screen. So I'm just going to enter this here, and notice that the sought current will not impede that transformation because the same current exists in both of those elements at the same time. So that's not going to be an issue. So I can replace 8 by 8 plus J56. And then I'll change this one to a short. And also, we'll change this to a generalized impedance. And since my dialog box is not handy right now, I will change that to an impedance here, generic impedance. Okay, so now we have to check that. So I'll just go over here and check the combination. And that's correct. And now we've simplified as much as we can do without killing sources, since this isn't in series or parallel with this element. So we're done editing. Okay, so now we need to go into the kill sources phase of the problem. So I'm going to go into the source killing mode of the circuit editor. It says right there I'm in source killing mode. And so now I'm going to turn off one of the two sources. It doesn't matter which one I do first. So let's kill the current source first. So we'll select that. And remember, a current source, to turn it off, must have 0 amps. That is, it must be replaced by an open circuit, which I can do by just simply deleting it. So I can press the delete key, for example. And then I'll check that I'm done by clicking Done Killing Sources. Okay, so that's fine. And now I need to analyze this child circuit for the value of I naught prime. Notice that this has automatically been labeled for us now as I naught prime. This is not the original value of I naught, it's a portion of that. So this is a single loop circuit. So I will use single loop analysis, and I can write, well, you know, I could have actually combined these two. I didn't think of that. And actually, that would be a little bit easier. So I'm going to go back into the circuit editor since I neglected to combine those two. So let's do that. So that would actually make this a J51. That's actually going to be a little bit easier. And short that one. That's certainly a good idea if we can do that. Okay, so now, again, single loop. Actually, I think in this case it would be easier to do this as single node pair because it's actually both. And if you choose the less favored form, it'll tell you that. So we're going to choose a sought branch current here and just write an equation directly for that. So I naught prime is simply going to be the value of a voltage source divided by an impedance. And if we wanted to just enter the number directly, you could do that. You'd have to use then a calculator to compute it and enter it directly with this form, and that would save an extra step later, but I'm just going to enter it this way. So our voltage source now is 1 angle 0. So enter that there, and the impedance is the value of Z1, which is 8 plus J51. So we'll just type that. Oops, plus J51. And now we always have to check polarity. Remember that P word. So let's think about this. The positive side of the voltage is on this side, and the negative side of the voltage source is on this side. So that means that we are in fact using basically a passive sign convention for this element. Since it has the positive voltage here and the negative voltage there, that is passive sign convention. So it means we'll have a plus sign in this type of formula. If the sought current had been reversed or the sign of the voltage source had been reversed, then we'd have a negative sign. So that very easily could have happened here. It just didn't happen to in this particular problem. But always be very careful about polarity or you'll get a lot of things wrong. Okay, so we'll check that. And that is correct because we remembered the right polarity. And now we've written the only equation we need to find I naught, so we'll click no more equations. Sometimes there might be more than that, but okay. Now we need to enter a numerical value just using our calculator for that, since we didn't enter it originally. And so I'm going to, to minimize that. So I'm going to use the calculator here. And so basically now I need to compute 1 divided by the value z1. So that will be a parenthesis. And that is 8 plus j51, which of course I enter as I51 here. And again, I want this now in polar form, and I'm actually in rectangular form. So before I click enter there, I'm just going to save myself a little extra trouble and go and change the mode right away. Since I want my number in polar form, it's best to change that mode before I do anything else. So I'll enter there and clear. And now I can just enter this and get the answer directly in polar form. Okay, so now I'll enter that into my form here. So I have 0.01937. And then the phase angle there will be negative 81.09 degrees. And notice that I am in degree mode here, so that did show in degree mode. And we'll check that answer. And that is correct. So now, okay, we've done that. We've finished analyzing the circuit with a single source active, which was the V1S source, and that result is recorded here for reference. But we now have to analyze for the other source. So I have to dismiss that dialog box to maximize this. And so now we've already simplified, so we now just need to kill sources again. And since we already have the value to the V1S source, we don't want to consider that one now. So that will be the one that we kill. Otherwise, we'd be considering it twice, which would certainly not work. So we're going to change that to a zero valued voltage source, which means changing it to a short circuit. So I'll just click on that, or we could have right-clicked and done it from the menu also. And that's all we need to do to kill sources. We certainly don't want to kill both sources at one time. And now we look and see what kind of circuit is this. Well, it's actually, if you think about it, a single node pair circuit. So we can directly use a current divider. We don't need to do any further simplification. Sometimes you might need to do additional simplification here, but in which case you could go into the circuit editor. But in this case, it isn't necessary. So I'm just going to go straight into single node pair analysis. And I want my SOT current, my I naught double prime. Notice that this has been relabeled as I naught double prime now because it's due to the second of the two sources. So I have a SOT branch current that I want to compute, and I can use the current divider formula, so I don't need any KCL equation or anything like that. So I'll set I naught double prime is equal to, and now I have several different things I could use. I could just put a value computed on the calculator in using this term if I want to do that. I could compute the voltage and put in the impedance, but I'm going to use one of the current divider formulas directly. And my own preference is for this particular formula, but again, you can use any of these three formulas are valid. Remember that the S here would be Siemens, so that would require the admittance in Siemens. So I think it's simplest, for me at least, to do it this way. So I'm going to put the value of the current source now, which is 9 angle 180 degrees. And then remember, in a current divider formula, we are going to have the other impedance in the numerator, because that's what will give us the correct current through this element. And basically the idea is that if the other one were bigger, for example, that means we should get most of the current through this element, and so putting a bigger number here would give us more current here, which would make sense. If we put this impedance and it were smaller than the other one, then we'd get less current, and then we'd be saying basically current takes the path of most resistance, which of course is not correct. Current tends to take the path of least resistance. So that's a way of helping remember that it's going to be the other impedance in the numerator of the current divider formula. So in that case, this is the negative J5. And we'll also put that down here. And then the Z1 impedance, go down here. That's 8 plus J56. That's notated below the circuit diagram since there might not be room for that long number on the circuit diagram. Okay, now we also have to always check polarity. Remember that P word. So let's think about where the current goes here. So the charge basically flows down through the current source, and then it's going to go, some of it's going to go back up that way to the current source, and other part of the charge is going to go down through here and back up. And notice that that charge will be going opposite to the defined direction of I naught double prime. So that means we do in fact need a negative sign in this case. So we could either put a negative sign here, or an alternative would be to change my angle of 180 to 0, because remember that 180-degree phase shift is equivalent to a negative sign when using complex numbers. So let's just do it that way for simplicity. And we'll check that equation. And that is indeed correct. So remember, if I didn't check the polarity there, I would undoubtedly, well, there'd be at least a 50% chance I'd get the wrong answer. So it's always important to check those polarities. Okay, so now we have a formula, and that's all we need, because that's what we're trying to get, is that I naught double prime. So I click No More Equations. And now it just asks me to enter a numerical value for I naught double prime. So let's go to the calculator now. And now, again, I want my answer in polar form, so we'll verify that my calculator is already in polar mode. That will save a step of converting it. And so I need to enter the value. So 9 angle 0, that's just the same as a 9. And then we multiply that times negative J5. So I'll just put that in parentheses here. And there's other ways of doing this, but I mean, I could have just multiplied that out in my head too. Would just be probably as easy. I could have said that that's negative J45 would be fine too. But I'm just showing it this way to be more general. Divide then by the denominator. So I'll put parentheses around the denominator. And really, I can add that up in my head. So I'm just going to say 8. And then the J56 minus J5 will be J51. So it's just going to be 8 plus J51, or I51. And that just saves a little bit of writing there, just to combine that in our head. And then we can just push enter. And now we have the value in polar form, which we can enter directly into our form here. So we have 0.8717 to 4 digits accuracy. You want to have at least 3. I like to put in 4 just to be more accurate. So we have negative 171.1 degrees, and we'll check that. And indeed, that was correct. Okay, so now we need to use the superposition principle to find the value of the total sought quantity. And there's the two values that we've already determined. It's recorded them on the screen for us. So basically, we just need to add those two values together, which is what you do in superposition. And let's see, and I have those already here. However, remember that I couldn't use that number formatted that way. It won't accept it in the calculator. So what I'm going to do is do the original expressions. I'm just going to use a little trick here. Do that plus this original expression. And now just click enter, and that'll sort of recompute it. And so now we've added those two numbers. This one is, of course, very small compared to this one, so it didn't make a big difference. So our total in this case is going to be 0.8719. And the angle is negative 169.8 degrees. And we'll check that. And that is correct. And then the last step is to do the inverse phasor transform. I won't need the calculator for that because its omega is already in radians per second. It's already given to us as omega. So here I just put in the magnitude of the complex number becomes the amplitude of the cosine function. Remember, we always use a cosine function. And if you're doing it by hand, you have to just remember that, because that's what phasors are based on, is cosines. And that's an arbitrary choice, but it's what we use. And then the angle is going to be negative 170, which is the angle of the phasor. And then the omega is 20 radians per second. So we just put in 20 there. That doesn't have any metric prefix or anything, so it's just a number 20. If we did have to use metric prefix, metric prefixes are not accepted in these text boxes, so you would just write it out as a complete number then. And remember, when you're doing this by hand, don't forget the time, right? Don't forget the t, because if there's no t, it's not a function of t, and that wouldn't make any sense at all, because this is supposed to be a function of time, because we are in the time domain. So let's check that. Okay, that's good. And basically we finished that, and if we want to see a complete explanation similar to the example before, we could click yes there, and it would show us all the steps involved in doing the calculation. Just in case we were uncertain about anything or any of the explanations, we could look at that. So that completes this problem.